Welcome back. All right, so Coulomb's law. So we are interested with this Coulomb's law in trying to figure out what is the actual force between two charges that are a certain distance apart. So within here, we are utilizing R, although you can certainly utilize D for distance in between. Now, we're going to assume, that our charges that we have, so these particular charges, are concentrated almost like at, point balls, that we have. So they're basically just pinpoint balls. So the charge isn't too big relative with respect to this particular distance in between them. So what we have is the following. So we have one charge, we have another charge. They have a certain distance in between them right here. So that is the R. This is your Q1. This is your Q2. And we want to know what is the force between these two charges. Before I dive into going in this equation a little bit deeper, I want to bring you back to Newton's law of gravity. Because if you relate back, and I have actually purposely, left it right here. So if you recall, when you're studying Newton's law of gravity, now these are only attractive forces between two masses, right? So we had mass number 1 and mass number 2. They were a certain distance, apart from each other. So notice we have a square, right there. And then there's a constant right here. So that particular constant, we find by experimentation. And that constant is a very tiny constant. And it relates things back for us. And we know what the force of attraction is between two masses. Now, when you're talking about matter and the law of gravity that Newton has come up with, that particular force is always attractive. So the force is always towards each other. But look at the enormous resemblance between this particular equation that we have here and Coulomb's law, which is also a force, but it's an electrostatic force in between two charges. So instead of talking about masses, as we did in the law of gravity, now we're talking about two charges. Now, we do have an absolute value, although most of the time those absolute values might be dropped, right? So you might not actually see those absolute values in the equation that your teacher might present to you, or you might be reading in a book. But technically, I like to put these within here just as a reminder, especially as I'm introducing this, because what it means is that masses are always positive. But as you know, charges can be either positive or negative. And within here, so we are just simply finding out what the magnitude of that particular force is. Now, this E just stands for electrostatic force, and it is between two separate charges. And we can find out what that will be. Now, instead of a capital G in here, which was the gravitational constant, here we have a K. And that constant, K, is actually much, much bigger, so notice, in comparison to this right here. So this is 10 to the negative 11, while this is 10 to the 9. So it's enormously bigger, right? So in terms of exponents, you can go from one to the other. Basically, there's an order of 20, in there. The charges that you have in here, so these particular two charges, we are going to be assuming that they are in coulombs, right? So that is the metric standard for here. The distance between the two charges, and we are squaring it. So the further that you are, the smaller this particular force will be in its magnitude. And it really goes down pretty quickly because of the fact that it is squared. So the further that you are, and the closer that you are, well, the forces are much stronger. The further that you are, they really taper off quite quickly. So now, when you are studying this, you have two, right? We have an attractive force, and that attractive force is in the case when these two charges are of opposite sign, so a positive and a negative, and they are repelling each other, so that force, is a repulsion force, and you would have that whenever these two are alike, so either two negative charges or two positive charges. And we can find out exactly what these would be. So let's take a look and just kind of briefly talk about this with a very simple example so that you can get used to utilizing this Coulomb's law in order to solve various forces. And I'll also talk about the fact that, well, we can bring in superposition as you have seen actually in now numerous cases, probably one of them is when you're talking about waves, right? So you can actually do the superposition of waves, okay? You can do the superposition here in terms of the charges, okay, and the force on a particular charge. And here's an example that we want to be able to utilize this Coulomb's law. So we have two charges. So here's the first one, okay, so notice it's positive, okay? Here's the second one, okay, which is also positive. So right away we know that the force, okay, so for example on this charge, coming from this charge is going to be in the opposite direction because they are repelling each other. And then there's also an equal and opposite force, okay, which is going to be on that. So if I want, okay, so for the moment, okay, let's just find out what is the force on this charge coming from this charge, which is 2.5 centimeters away. So it's not very difficult to be able to utilize Coulomb's law in terms of the formula itself. So what we would do is, so this is the actual electrostatic force which is present, and it is equivalent to, so now notice K multiplied by, now it's going to be your charge 1 multiplied by charge 2, okay, so within here, and then divided by the distance, okay, which is going to be squared. So if you're going to be substituting all of this in, okay, so this is going to be for your charge, this is going to be for your charge, okay, we know that K, so that constant K is right there, so it's a rather big constant, okay, that we have. And that constant, okay, so you can substitute it back into here, and then this is the last one, which is just the radius. So for us, please don't forget, we want to be able to change it to metric standard units. So have your charges in coulombs, and then your distance in between them to have it in meters. So I'm going to do the quick calculation, which is just substituting this in, and let's see what that particular force will be. All right, so there you have it. Okay, so that is 1.86992 newtons. Of course, we can just take this. I'm just taking a peek, so I'll just keep it to two significant figures. So, for example, 1.9 newtons. All right, so that is the force. And now, in which direction is this? Well, so this particular force is going to be in this direction. It's going to be trying to repel this out. So you're going to have 1.9 newtons, okay, going in here. Now, if you were thinking about the other charge, okay, so this one, well, it's going to have exactly the same amount of force, but it's going to be in the opposite direction. So that's how you can apply Coulomb's law. Now, if the charges are positive and negative, so notice that's why, we sometimes will put absolute values, okay, within it, just so that we can calculate the magnitude of this, and then we ourselves decide, okay, what is the direction. And the direction is not very difficult because it's either attractive or it is repelling. So the other component, okay, that I mentioned was superposition. And when you only have two charges, then this equation just works. But now what happens if you have multiple charges? What if you have 3 charges or 4 charges? So how would you actually apply that? Well, so the way that we do this, so within superposition, okay, so the principle of superposition, that comes from the fact that you can apply the actual equation, so Coulomb's law, individually, okay, to all of the actual forces. So for example, if I would call, so instead of calling this just Fe, okay, if I would call that this is the force, okay, that is on Q1 coming from Q2, and that would have been the first one. So I'll do that, and if I wanted to have another charge, then what we would do is that we find the net force. And the net force is going to be the addition or the superposition of all of the forces. So I'm going to just do it with respect to, for instance, what are all the forces that are present on this charge? Well, on this charge, I'm going to have this present if there is only one particular charge. But if there are multiple charges, then what you can do is, so for instance, if I would have placed another charge in here, so somewhere along the way, okay, so let's say I put another charge somewhere over here, okay, so this is what we would have, and I'm going to call this charge Q3, and let's say Q3 is equal to, maybe let's make it negative, okay, this time around, so let's say it's maybe negative, 1.5 times 10 to the maybe -6 again, right there. So that would have been that charge. So as soon as I do that, it doesn't erase the fact that I have found this particular force, right? So that would have been the first force that is found on it, and we know that it's to the left. Well, in this case, it's to the left because it's repelling it. But then I can add now the second force, which is going to be F on Q1, but it is coming from Q3. And if I had more of these charges, I could just keep adding them together. And that is called the superposition principle, where I can do them one at a time. So I don't have to worry and stress out about all of these. Remember, these are just vectors. So you can find each force as a vector individually, and then you can start adding them up. So for instance, okay, if this was the case, now I do need to know what the distance might be here. So in between, for instance, here and here, so what that distance might be. So I'm just going to kind of make it up, okay, as I kind of go along. Let's, imagine maybe it's 1.8 centimeters right there. So what I would have is that this force is going to be equal to, still by K, now it's going to be Q1 multiplied by Q3. Now it's the absolute value, so the negative will just kind of be gone, divided by, within here, so the distance in between them. So now in this case, the distance is, sorry, I forgot, 1.8. All right, so I'm going to put it back in, okay, into metric standards. And that's how you would calculate it. So you're going to find out what the force is. So I'm going to do that very quickly, and let's see what it is. All right, so there we have it. So that would have been the next one. So maybe I'll just round this off. Actually, I won't round it off because I want to be able to just show you, okay, so what happens here. So in this case, we have our second force. So this, notice that it's bigger. Now, of course, it's closer, okay, to our charge that we have it, and it is a little bit bigger in size. So what happens now in this case is we have these two forces, okay, that are present. So on Q1, so if this is Q1, you can now draw these forces. So you have one force, which is approximately 1.9 newtons, and then this one, which is, about twice as big, and this one goes in this direction. This one is approximately 4.2 newtons, right? And now you just have to add the two forces, right? Now the addition is vector addition. So we're just adding up the vectors, so, be careful. So what that would mean is, I would have my result right here, and because the other one is in the opposite direction, then really it's just a subtraction, and it's a subtraction. I'm going to use the full numbers there, so 1.86992. Okay, and that's going to give me the result. So that result right here is this value. So this would have been approximately, I guess, 2.3 newtons, and it is to the right. Okay, and we utilize the superposition, so just the addition of individual kind of forces that are present. So you can do that, on multiple forces. You can add a third force, fourth force, etc. And you can, of course, make these more complicated, where you don't have to have them in a line, so they're not linear, okay, within the same kind of same line, which is one-dimensional. They can be all over. They can be two-dimensional, but you're going to have to utilize trigonometry in that cases. And I'll do an example of that. I'll put up a link up above there. Once it's finished, you can take a peek at it. So there you have it, okay? So you have now kind of been exposed to Coulomb's law, okay? You've seen an example, both kind of one example with one charge, and now what happens with multiple charges. So keep in mind, just use them as vectors, and then understand the directions that they're pointing, and then what you have to do in order to solve it. All right, so thanks for watching. We'll see you in a future video. Happy studying, everyone.